talk about in this unit is logarithmic and exponential equations. So we have actually already talked about logarithmic equations, or sorry, exponential equations rather, because we've solved something like 5 to the x equals 25, right? X has to equal 2. But the types of exponential equations that we've solved so far have been ones where we can change the base. And so we're going to bring in some exponential equations today that you can't solve by changing the base. And what we're going to do is we're going to use logarithms to solve them. Okay? So the idea, firstly, a logarithmic equation is an equation that involves a logarithm where the variable is typically somewhere in the argument. So here, for example, this guy down here, there's an n plus 9 in the argument. That would be an example of a logarithmic equation. Okay? Exponential equation is when the variable is in the exponent position. Okay? But what we've sort of already seen is that we can switch something from logarithmic form to exponential and vice versa. And so the position of that variable may move around. Okay? When you are using logs to solve, or when you're solving a logarithmic equation, there's essentially two strategies that you want to try and think about. One, you can combine logarithms using log laws. To get an equation that looks like this. Log of A equals log of B. Okay? And if you can have a single logarithm on each side, you can drop the logs and conclude that A equals B. Okay, so that's one strategy. And depending on the question, we may need to use this or something else or multiple strategies all at once. Okay, so that's one thing that we might be doing. The second thing that we might be doing is looking at an exponential equation and switching forms. That might help us solve the equation. And then the other strategy that we might use is to, if we have something equals something else, we can take the logarithm of both sides, and we should have that the logarithm of that something equals the logarithm of something else. Okay? So we might use that strategy as well. Sometimes we have options. Okay? Now, just one thing that we're going to need to think about when we solve logarithmic equations, particularly when you're doing the first one, this guy, is that in the process of dropping the logarithms, you change the nature of the equation. It is no longer logarithmic. What we will see is it will most likely be either linear or quadratic. And so we're going to then have to solve that equation instead. But we have essentially swapped from a logarithmic equation to now a linear or quadratic equation. Whenever you change the nature of an equation, there is a potential for extraneous solutions. So that is something else that we're going to have to keep in mind. Okay? And when we get there, we'll get there. But that's just sort of the overarching main ideas. Okay? So let's start with something pretty simple. Here we've got log of n plus 9 equals log of 4n. So we already have the format log equals log. Okay? If we have that format, we can conclude, and especially, the bases have to be the same, that n plus 9 has to equal 4n. Okay? It's almost like dropping bases when you're working with an exponential equation. And now this is linear, so we can solve this. I'm going to maybe subtract n from both sides, and I'm going to get 9 equals 3n. So n equals 3. Okay? Now, one thing to do is to check to make sure that if n equals 3, that both arguments are positive, right? So I'm just going to do a quick check. Okay, 3 plus 9 is 12. 4 times 3 is 12. That's fine. Okay? All right. So now let's get into the more challenging stuff. And a lot of these are going to end up being exponential equations where we're going to have to use logarithms to solve them. And when you are solving these types of equations, often you have options as to different strategies to take. So, and the options usually are switch to log form or take the log of both sides. So what I want to do actually is for each of these equations, show you different options that you can use to solve them. Okay? So the first thing that I'm going to do in this particular equation, this is exponential. I'm going to check before I do anything that I can't solve this by changing the base. Right? So I'm asking, okay, could I write 4 using a base of 3? And in this case, I can't. Okay? So that's one thing to check because you're not necessarily going to have like solve this exponential equation using logarithms, right? You may just need to know, oh, I can't write that as a power of 3, so I'm going to have to use logs here. Okay? So method 1. Okay? Take log of both sides. Okay? So if I have 3 to the x equals 4, I should have actually spread that out a little bit more. I'm going to give myself some space. Then the log of 3 to the x should equal the log of 4. Okay? All right, now ultimately my goal is to solve for x. And right now it's still in the exponent position. So what's a step that I could take? Yeah. Yeah, so we can use our power law, right? We want to essentially take this variable out of the exponent position. So I'm going to have x times log 3 equals log 4. Okay? Now what? Yep.
Isolate x.
Yeah, so isolate x by doing what?
Dividing log.
Yeah, divide both sides by log 3. Okay, so we're going to get x equals log 4 over log 3. This, by the way, is not the same as log of 4 over 3. Okay, they're very different. Now, you could put this into your calculator if you want and get a decimal approximation. That would be the same decimal approximation that you would get if you solved this graphically, right? y1 equals 3 to the x, y2 equals 4, get the x value of the intersection point. But this is an algebraic solution. So if I go log 4 divided by log 3, that's about 1.26. Okay? Now, another thing that I really want to emphasize is that one of these solutions is exact and one of them is approximate. So pay close attention to what you're asked for. If you're asked for an exact solution to this type of an equation, I want this because this one has been rounded. Okay? Another thing, if I ask for an exact solution, if I say solve, give an exact solution, that is also an indication that something has to be done algebraically. Because if you solve graphically, you're always going to get an approximate solution. Okay? So make sure you're just aware of what's being asked for and you know the difference between the two, right? Approximate is whenever you plug it into your calculator and get a decimal and round at some point. Okay? All right, that's one strategy. Method 2. Okay, we can switch forms. So if I start out with 3 to the x equals 4, this is in exponential form. I can put this into logarithmic form. The base of the log will be the same as the base of the exponent, so that will be 3. Okay. The argument is the value of that power, so that's 4. That equals x. Solved. Okay. This is an exact solution. You do need to remember your change of base law, however, because firstly, I know a lot of you guys have figured out that you can enter in whatever base you want into your calculator. Okay. So if you have that feature, great, use it, no problem. But if this was a multiple choice question, for example, you will probably get the solution using base 10. So you need to know that that's equal to log 4 over log 3 so that you can match them up. Okay? Or it might be a numeric where it's like, it can be written as log A over log B. What's the value of A and B? That kind of thing. Okay? And that we plug that into our calculator. It's the same answer. Okay. Just curious, so far, how many people think they'd prefer doing it this way? Okay, how many people think they'd prefer doing it this way? Okay, cool. Some people just don't care, I guess. It's funny, like, I don't think, I can't honestly remember, but I feel like I never learned this way, switching forms, right? And it's probably because that feature of being able to put in whatever base you want into a calculator is pretty new, right? And it's just an algorithm that's in the calculator. It's like programmed into the calculator, but it's change of base. Yeah, but I always did this when I learned, so that's probably why my instinct says to take the log of both sides. But you can do it whichever way you want. They're both algebraic solutions. Okay, here's another one. Now, before I do anything with this equation, I'm going to do one thing first. What do you think I should do first? Say that again? What do you mean by apply the 8? We got to do something with that 8. Yeah. Yeah. Divide both sides by 8. Because whether you're taking the log of both sides or you are switching forms, particularly if you're switching forms, you need the power to be isolated. Okay? So I'm going to divide both sides by 8 first, and I will get 3 to the 2x equals, is that 71? Okay, because 560 divided by 8 is 70. 71. Okay, now this looks very, very similar to what we just saw. So at this point, you could take the log of both sides. I'm going to do both methods. You'll divide them down the middle. Okay, so I'm just going to stick a log there and a log there. Okay, I can take this guy, pull it out in front. So I'll have 2x times log 3 equals log of 71. And then to isolate x, yeah, we need to divide by log 3, but we got to divide by something else too. 2, yes. Right? We're going to divide both sides by 2 log 3. And then the log 3's will cancel and the 2's will cancel. So x is equal to, I should probably write it out nicely, log 71 over 2 log 3. Okay, now if you want a decimal approximation for that, log of 71, oh, whoops, bracket. When you're dividing by 2 log 3, make sure that that 2 times log 3 is in brackets, okay? Because otherwise it'll just divide by 2 and then multiply by log 3. So divided by 2 times log 3. And then I'll close those brackets. And that is about 1.94. Now, if we are solving this by switching forms, still divide by 8. Particularly if you're switching forms, you need the power to be isolated. So this will be 3 to the 2x equals 71. And then I'm going to switch to logarithmic form. So the base of my log is 3, same as the base of the exponent. The argument is 71, and that's equal to 2x. Okay? And then I can divide both sides by 2. And I have x equals log base 3 of 71 over 2. If you're asked for an exact solution, that's fine. You don't have to make it base 10 if you're asked for an exact solution. If you were to switch this to base 10, it would be log of 71 over log 3 over 2. And that's the same, right? This can actually come down. So you end up with the same value. You look like that's a little confusing. Do you guys know why this can come down? When you have this type of fraction, the denominator of the numerator can come down, because essentially what you're doing is, and I do want to show this because we might be using this a lot, is you are taking a fraction and dividing it by another fraction, right? So log of 71 over log 3, you would take that and multiply by the reciprocal times 1/2. And that becomes in the numerator log of 71 over 2 log 3. Okay, so that denominator that's in here can just come down. Okay? Okay, questions so far? All right. So we're going to take it up a notch. Okay. These ones are more challenging. And I will show you both ways of doing this. I actually shouldn't. I was going to say that I would recommend that you take the log of both sides when you have variables in both exponents. But you could do it the other way too. So let's look at it. You guys can be the judge of what you want to do. Okay, so here we go. So I'm going to start by taking the log of both sides. And taking the log of both sides, because of that power rule, it allows us to get that variable out of the exponent position. And that's what we need if we want to isolate it. Okay? So that's going to be my first step. Now I'm going to take these guys, bring those in front. Okay, so I'm going to end up with 2x minus 1 times log 3 equals 3x plus 2 times log 4. Okay. Now, this is actually a linear equation. Okay? Because I'm taking 2x minus 1, multiplying it by a number. Happens to be an irrational number, but it's still a number. And then I'm taking 3x plus 2, multiplying it by another number. So when we're solving a linear equation, if I had this times 5 equals 3x plus 2 times 2, something like that, right? Same format. It's just that instead of the 5 and the 2, and I just made those up, I'm multiplying by these irrational numbers, which are logarithms. Okay? What would you do here if you wanted to solve these?
Expand the 5.
Yeah, multiply this in, right? So that's what we're going to do here. We're going to have 2x times log 3 minus log 3. And then on this side, we're going to have 3x log 4 plus 2 log 4. Okay, so if we were to do that, here we would have like 10x minus 5 equals 6x plus 4. Okay, so if, I've expanded the 5 into the left side and the 2 into the right side. So what would you do for this linear equation now? Yeah, we want to isolate x. So before we can say x equals this, what would you do? Let's solve this. What's that? Yeah? Okay. How are we going to do that? Yeah. Collect x terms on one side, collect the numbers on the other. Okay? So if we look at this, these are the ones that have an x in them. And these are the ones that are just numbers. So we need to collect x's on one side. So let's say I subtract 6x. Ooh, that's very thick. Okay? Okay. Now I'm also at the same time going to add 5 to both sides so that my numbers are all on my right. And I have here 10x minus 6x is 4x. Negative 5 plus 5 is 0. Equals this is 0, 9. Okay? So let's do the same thing here. So essentially, when I move something in a linear equation to the opposite side, it's just going to change signs, right? Are you guys okay with that? So I'm going to bring this over, and it's going to be negative minus 3x log 4. And then when I bring this over to this side, it's going to become positive, because I have to add it to both sides. Equals 2 log 4 plus log 3. Okay, so I've rearranged my equation so that the x terms are on one side and the numbers are on the other. But now I have to do something else. I can't just divide, like here, now I can just divide by 4, right? Can't do that here because I'm multiplying x by these irrational numbers. So what I'm going to do is I'm going to factor the x out. Okay, so here I'm going to factor. I can pull a factor of x out of here, and I'll be left with 2 log 3. And I can pull a factor out of x out of here, and I'm left with minus 3 log 4. Okay. Stop me if there's any part that doesn't make sense. Yeah?
Isn't it 2x, you have to pull up 2 x's? Or you only pull up 1 x?
So basically what's happening is I'm going 2 times x times log 3. If I pull the x out, I'm left with these two factors.
So just x by itself, not 2x?
Yeah, because I didn't factor out a 2. I just factored out the x.
Isn't it 2x though? Just 2 x's.
Think about it multiplying this back in. X times 2 log 3 is 2x log 3. Right? So if all I factor out is this and this, these two factors remain. And these two factors remain. If I took out a 2x, this would have to be 1.5, because I'd have to take a 2 out of here too. Yes?
In theory, if you had to because wouldn't you if you were to redistribute the x, you'd have 2x log 3x.
You'd have 2x log 3 minus 3x log 4.
But why does the x only go to the 2 and the 3 then?
Oh, it could go in any order, right?
No, but technically, if you're redistributing, I can't think of a question, but normally when we had that.
Because it's going into the a value, it's not going into the logarithm itself.
Oh, I see what you mean. Why does it not go to the log 3 as well?
Yeah, I know,
Okay,
I know that
good question.
obviously it does.
Yeah. Okay, so let's say I have 2 times 3 times x, or I'll just even reorder this. Because it's the same x times 3 minus 5 times x times 7. Okay, same sort of format. If I were to pull an x out and say, okay, well, what's left over? If I divide this by x, I'm going to be left with 2 times 3. And if I divide this by x, I'm going to be left with 5 times 7. It's just, I know it's confusing because it seems like this should be a variable, but it's not. It's a number. We can get a decimal approximation for it. Okay. If I were to expand this back in, would it be more helpful if I did this? If I reversed the order and wrote this as x, x times 2 log 3 minus x times 3 log 4. Okay, let's do that. Okay. Bottom line is, though, once the x is factored out, now I have something that I can divide by on both sides to isolate x. So what I'm going to do is I'm going to divide both sides by this bracket. And I've isolated x. These cancel. So this is my answer. Again, if you're looking for a decimal approximation, it's really important that the entire numerator goes in a set of brackets and the entire denominator goes in a set of brackets, okay? So, because people will make errors with that. I can't even remember what it was so long. 2 log 4. Oh, I just did it. I didn't put the bracket in. 2 log 4 plus 2 log 3 plus minus, 2 log 4 plus log 3. Best to have it out in front of you. Divided by 2 log 3 minus 3 log 4. Whoops, bracket. Okay, so that's about negative 1.97. Okay, guys. This type of equation is sort of as hard as it gets. But yeah, like it's a lot, right? And I think a lot of times the hardest piece to wrap your head around is the fact that that log 3, log 4, log of whatever, that's a number. Okay? Okay. One thing I will say, though, is that they do become really repetitive. Shh. So, if you're solving something like this, where binomial, the steps are going to be the same every single time. So if you practice it 4 or 5 times, you'll have it down. Okay? Do you guys want to talk about how to do it the other way? You're like, no. Which is to switch forms. Okay, can I tell you why I wouldn't switch forms with this one? Okay. The reason why I wouldn't switch forms is because there's variables in both, on both sides, in both exponents, right? When you switch forms, it's really nice to do that when you have a variable on one side, like here, because then you can get that variable out of the exponent position when you switch forms, and this side's just a number, right? That's pretty nice. But when there's exponents on both sides,
Ryan Leclerc and Sparrow,
like here?
can you please return to your classroom? Ryan Leclerc and Sparrow, return to your class, please. Thank you.
when you have exponents on both sides, you're going to kind of be doing both at the same time. When you switch forms, you're going to have exponent on one side and then still have to bring that exponent out on the other side, and so it gets a little messy. But we could totally do it. I have it in the completed notes if you want to take a look. What do you say?
Look at it.
No, you'll look at it? Okay. All right. Let's look at this one. Okay. What about if do you guys want to try this one by switching forms? Okay, let's switch forms with this one. So this would be the second method. Okay. Now, if I was switching forms here, do you see how there's exponents with variables on both sides? Okay. I actually can only isolate one of them. Right? So if you think about this exchange, okay? If I was going to make an effort, right, like when the exponent is here, you can isolate it and set it equal to a logarithm, okay? Here I've got them on both sides, so sometimes you have an option. In fact, in the previous question, you could have isolated either one when you put it into logarithmic form. But in this case, because of this little pesky 3, this has to be treated as the argument. And this guy would be the power. So we would have to isolate this x. Okay, now I'm just rethinking my thoughts here. We can do this the other method, which is to switch forms. But honestly, if I was doing it, I would never, ever do it that way. So are you guys okay with just taking logs of both sides? Okay, let's do that. I think it makes a lot more sense. Okay, oh, I switched pages. Oh no, I didn't. Where did it go? Did I ditch a page? Did I reorder? No. Where'd it go? I lost the question. I deleted it. Wait, yeah. Maybe you guys want me to delete the question. Okay, so look, yeah. With this question, I would never switch forms. And in fact, personally, I would only switch forms if there's only a variable in one exponent and not in both sides. Okay, so let's do it. Okay, so I'm going to take the log equals log 7 to the x. Okay, now the purpose of taking the log of both sides is that I can take this exponent and bring it out in front. So I can do that on the right side. Can I do that here? No. What do I have to do first? Well, okay, I can't times the 3 by the 2 because then I'd be doing multiplication before exponents. But yes, it has to do with the fact that these are being multiplied together and that x plus 1 only applies to the 2. But I could break it apart, right? I can break this up into the sum of two logarithms. So I'm going to make this log 3 plus log 2 to the x plus 1. And now I can bring this out in front here. Okay, so I'm going to have log 3 plus x plus 1 log 2 equals x log 7. Okay. Where do you think I'd go next? Yeah. Okay. So I could do that, right? And I can see where it would be really sort of enticing to do that, because then you have x isolated, but you'll have x in terms of x, because there's going to be an x in this side. And essentially, you want x on one side, numbers on the other. These are numbers, right? So this is essentially the same as something like 5 plus x plus 1 times 8 equals 13, or x times 13. That's the same structure of that equation. It's just that instead of 5, 8, and 13, I have logarithms, which are irrational numbers. But what would you do here? Yeah? Okay, so that's the same sort of thing that Logarithmic was saying. If I divide by 13, right, I'm going to have x equals this, but I'm still going to have an x on that side. Right? Yeah?
Can you distribute the log?
Yes. Distribute, expand. Okay, so whenever you have brackets like this, expand everything. Okay? So we take logs to have the ability of using the power rule to bring the exponent out in front. Once we bring that exponent out in front, if anything's in brackets, expand it all out. So we're going to have x log 2. So x times log 2 is x log 2. And then plus 1 log 2, or just log 2, equals x log 7. Okay? Now what? Yes, subtract it, right? When you're solving linear equation, collect x terms. So once everything's expanded, collect x terms on one side, collect numbers on the other. So these are both numbers, but this is an x term. So I'm going to subtract x log 2 from both sides. Okay? So on the left side, all I'm left with is log 3 plus log 2. On the right side, I can now factor out an x. If I factor an x out of here, I'm going to be left with log 7. And if I factor an x out of here, I'm going to be left with, minus log 2. Okay? And now I can divide by this number, whatever that is. It's an irrational number. Okay? So these cancel. And x is equal to that guy. Log 3 plus log 2 over log 7 minus log 2. Okay, now, just to save us some time, I'm not going to go and get the decimal approximation of that. You guys can punch that into your calculator yourself. Just make sure, again, that when you put it in your calculator, you have brackets around the entire numerator and entire denominator. Okay? We're almost there. I think. Do I have another one after that? Oh, I do. Okay. We may have to finish some of this tomorrow. That's okay. Okay. So when you have these logarithmic equations, what we had solved is except for the very first question, everything was exponential. And we took logarithms on both sides to be able to isolate the variable. And the key, again, is that if the variable is in the exponent position, if we take logs, we can use that power law to bring it out in front. And that helps us isolate the variable. Okay? When you have a logarithmic equation, like this one, the ultimate goal is to have a log equal to a log. And so we want to be able to use our log laws to get there. Okay? Now the problem is if this was a logarithm with base 7, we could use a quotient rule here. Guys, I know you may be on topic, but it's really distracting for me when there's these side conversations going on. Okay? So if this was a logarithm with base 7, I could use a quotient rule here, and then I'd have log equals log. Okay? I can transform 1 into a logarithm with base 7, though, because log base 7 of 7 to the 1 is equal to 1. So I'm going to start with that. So log base 7 of 7 to the 0 would be 0. But then this would be a 1.
Oh.
Yeah? Okay. Okay. And now I can use the quotient law to combine the right side into a single logarithm. So I'm going to have log base 7 of x plus 4 equals log base 7 of 7 over x minus 2. Okay? And now I can drop the logs. Because I have log equals log, they have the same base. And so I can just say x plus 4 has to equal 7 over x minus 2. Okay? Now, when we did this, though, we changed the equation from logarithmic to rational. This is now a rational equation. And in fact, we're going to change it one more time into a quadratic equation in a minute. But you have to think about extraneous roots, okay? So if we look at the two individual logarithms, here for this to be positive, x has to be greater than negative 4. Okay, so let's think about that. Here, x has to be greater than negative 4. With this one, for it to be positive, x has to be greater than 2. Okay? At the end of the day, which of these is more restrictive? Yeah. So the one that's more restrictive is the one that covers less of the number line, right? So this is a smaller domain. So you have to go with the smaller of the two. Okay? Okay, so let's keep that in mind. What would you do next to solve this equation? Yeah, multiply both sides by x minus 2. Okay? Okay, so now we have a quadratic equation. So we can expand out the left side because this side doesn't equal 0, so we can't solve it yet. But we can expand this out. We're going to get x times x is x squared, and then plus 4x minus 2x is plus 2x. Negative 2 times 4 is minus 8 equals 7. Okay? All right. What next? Yeah, subtract 7 from both sides. If it's quadratic, equate one side to 0. And then either factor, if possible. This one is factorable. Or you may have to use the quadratic formula. We don't usually give you those because that's kind of mean. But it is a possibility. Okay. All right, so we're looking for two numbers that multiply to negative 15 and add to 2. What would those two numbers be? Yeah.
5 and negative 3.
Right. X plus 5, x minus 3. So here we're going to get x equals negative 5, and here we're going to get x equals 3. Okay? Is that it? Are those my solutions? This is extraneous. Yeah. So take that, cross it out. That's extraneous. Okay, so this is the answer. You know, if you're asked for an algebraic solution to this, which you will be, you could also verify it graphically, though, if you're not sure of the restrictions in the extraneous roots. Graph the left side, graph the right side. You'll only get the one intersection point of x equals 3. Okay? All right, so I want to do this last question, and then we'll call it a day. Or we may even, I don't know, we'll see. We may not finish it, but let's see what we can do. Okay? So the ultimate goal is to make a log equal to a log. So what are some things that we can do? This needs to be condensed. That's not a logarithm. What are some things that we can do? Yeah. Quotient law on the left side, almost. This just has to get popped up here first to make that a 2, right? Yeah, so now we can use a quotient law. Log base 4 of x plus 4 squared over x plus 12 equals, what about on this side? Yep.
Log 4 x plus 12 plus 12.
So 1 would be equal to log base 4 of 4. Yeah, because this is 4 to the 1. Okay? Okay, so now we can drop the logs, and we can set the arguments equal to one another. And again, keep in mind, here x has to be greater than -4. Here x has to be greater than -12. Okay? So if you think about what covers more of the number line, yeah, it's this guy. We have to, in fact, you know what? I screwed up on the last one, didn't I? Didn't I? I did. This is the overall restriction.
Yeah, that's right.
Yeah. Sorry, that was my bad. Yeah. Okay, yeah. This one covers more of the number line. So this is the restriction. Whatever we get has to be bigger than -12. Okay? But now again, we have a rational equation. So where would you start solving this guy? Yeah, multiply both sides by x plus 12. Okay, so these cancel. And now we need to expand because we're going to have a quadratic equation. So we need to expand everything, equate one side to 0, and then see if we can either factor or use the quadratic formula. So x plus 4 squared, that's x plus 4 squared. Are you guys okay with that? Because I can, like, you know, x plus 4 squared is x plus 4 times x plus 4. So x times x is x squared, x times 4 is 4x, plus another 4x plus 16. Okay? And then on the right side, we have 4x plus 48. Okay? All right, now what? Yep. Subtract 4x and 48 from both sides. And the right side's 0, and then the left side is x squared plus 4x, and then minus 32. Okay, so this one does factor into, adds to 4, multiplies to -32. 8 and -4, right? Is that right? Okay. So what are the solutions here? Yeah, here we have x equals -8. So what's the solution? Not both, no. Because if x was -8 and you stuck it in here, this would be negative. You'd be taking the logarithm of a negative number. Okay? So it's only x equals 4. This guy is extraneous. Yes?
What is the math behind a logarithm?
Say that again?
What is the math behind a logarithm?
The math behind a logarithm
One
is
plus 1 equals 2. But what is log?
1 plus 1 equals 2.
Like a plus sign, you add two things together.
Yes.
What does a log do?
A logarithm basically tries to get you to figure out what exponent to this base equals the argument, right? It's a valid question. I said this at the beginning, but I'm going to say it again. Why do we use them? We use them when we're comparing values that have an enormous range, because we don't want to have to keep track of the actual value. We want to be able to just keep track of its exponent, because we're working with a smaller number, right? So things like the Richter scale. One earthquake can vary in intensity by an enormous amount to another one. Or pH, where we're looking at the concentration of the hydrogen ion. That's really what they're good for. Okay?
But is it like multiplication behind it? Or
So when you have log base A of B, A to the power what? Equals B. You're looking for an exponent on this base that gives you a value of B. Okay. Just hold on a sec.